Okay, we are live. Good afternoon, everyone. Welcome to another talk of Valongo Observatory. And today we have the great pleasure of having with us Natalia Guerrero. I'm sorry, Natalia, my Spanish is not perfect. So just so you guys get to know Natalia a little bit better, she is the TESS Objects of Interest Manager and the MIT TESS Communications Lead in the TESS Science Office at the Massachusetts Institute of Technology in Cambridge, Massachusetts, the famous MIT. Prior to the TESS launch in April 2018, she contributed to the performance testing of the 4 flight cameras for the mission. And Natalia also studied physics and writing at MIT and graduated in 2014. So Natalia, welcome to our seminars. It's a great pleasure to have you here to hear a little bit more about the incredible results of this great mission, TESS. And thank you very much for accepting our invitation. So I'll put here your presentation on the screen. We can already see your first slide. So the floor is yours. Thank you very much.
Thank you very much. I'm really honored to be here, and boa tarde to everyone. So my name is Natalia Guerrero, and I work at MIT in Cambridge, Massachusetts in the United States on this NASA spacecraft called TESS, which stands for the Transiting Exoplanet Survey Satellite. So this is the view of MIT from the top of one of the buildings where a lot of our exoplanet astronomers work. And you can see over in the right, this is where my office is, this little concrete building there. So I'll start by talking about the paper that was recently published from the TESS mission. So this is the TESS Objects of Interest Catalog from the TESS Prime mission. So as you can see, there's a lot of authors on this paper. It was just accepted to the Astrophysical Journal Supplement Series. So this is one of the TESS mission papers representing the catalog of exoplanet candidates that we have found in our first 2 years of science observations from TESS. And you can look it up on arXiv. I posted the arXiv number on this slide. So I'm going to spend the rest of this talk talking about what TESS is, what it's searching for, planets around other stars or exoplanets, and a little bit more of the details of what's actually in this catalog, what kind of exoplanet candidates we've discovered. And I'll conclude with talking about some of the highlight exoplanets and other non-exoplanets that we have found with TESS. So before I go on any further, I want to acknowledge that if it wasn't clear from the really long list of authors on this paper, this catalog is a team effort. I work with an amazing group of people in the TESS Science Office who all make this catalog possible. So I've shown their names and faces here. In addition, we have a TOI steering committee that's supported by the TESS Science Office, both at MIT and the Harvard Center for Astrophysics. Those are the names here on the left. We also have a huge team of individuals who look at hundreds of potential exoplanet candidates every single week, and that's the group of people over here on the right. There's a lot of names here. There's a lot of really committed, dedicated participants here. The people in orange are those who have joined the team most recently. And I'm really excited to say that many of these individuals are rising astronomers new to the field, and to be able to make such a valuable contribution to exoplanet astronomy so early on is, I think, one of the hallmarks of the TESS mission. So what is TESS? It is a space telescope that's about the size of a refrigerator that is currently orbiting the Earth in a highly elliptical orbit that takes about 13.7 days to complete. So TESS stares at one patch of the sky in its orbit, and at the end of its orbit, in this orange section here, it downlinks its data and goes on. This orbit is stabilized by resonance with the moon, shown in this orbit in gray. So TESS has been orbiting the Earth since its launch in April of 2018. So this is me at the launch pad in Cape Canaveral, which is on the eastern coast of Florida. This was a really exciting moment for the team. As it was mentioned in my bio, I was part of the camera testing team, so checking the performance of the test cameras before they were integrated onto the spacecraft and then launched, which was an exhilarating and a little bit terrifying moment for us all. So TESS launched in April 2018, and here we are having just celebrated TESS's third launch anniversary, is what we call it, 3 years later. So where are we at? What is TESS doing now? So TESS, I mentioned before, it has 4 wide-angle cameras that have their fields of view stacked to look at the sky. Each camera has a really wide field of view, 24 by 24 degrees. And we stack these fields of view one on top of the other to form a long strip or a sector. So overall, that's 24 by 96 degrees on the sky. And these sectors overlap first in the southern hemisphere of the sky, which we observe for 2 orbits, or about 27 days each. And so that was TESS's first year of observation, was observing the entire sky, or nearly the entire sky in the southern hemisphere, and then turning and observing the sky in the north. So on the top and bottom of these, there's 2 overlapping regions, the TESS continuous viewing zones, which have a total observation time of about 1 year. And this is really valuable for observing exoplanets that only transit their star a few times a year. So over the course of the TESS Prime mission, which took 2 years, TESS imaged the sky. I've shown this in this animation here, with 4 cameras, 13.7 days per orbit, 2 orbits a sector for 26 sectors. So we have a huge amount of data that we have taken, both full frame images, which are these images here, and then each sector, we take data every 2 minutes for a pre-selected list of 20,000 target stars. And so we have these small postage stamps, which I've shown here. So 30-minute full frame images. And then for a pre-selected list of 20,000 targets per sector, we have target pixel files that are taken every 2 minutes, which gives a really high cadence, finely detailed light curve for target stars imaged this way. So TESS has observed 70% of the sky in the last 2 years. So this is a huge amount of ground for this survey satellite to cover. And we have been searching for exoplanets in all of this data, both in the 30-minute images and in the 2-minute images. So before I delve into the nitty-gritty details of how we do that photometry and extract these light curves and search for these exoplanets, I wanted to give an overview of what it is that TESS has discovered in the broader context of exoplanet discovery thus far. So from other surveys, there have been thousands of transiting planets discovered. This includes Kepler, K2, and other ground-based surveys. So I've shown these here in orange dots. You can see the Kepler field here on the northern hemisphere and the clusters of K2 planets here along the ecliptic. TESS did not image the ecliptic in its prime mission. I'll talk a little bit about at the end about how it's going to observe parts of the ecliptic in its extended mission. So there are thousands of exoplanets that we have discovered in the last decade or so from Kepler and other missions. And so what has TESS added to that? In our first year, we added over 1,000 TOIs, or TESS objects of interest, just from the southern hemisphere. And then in our second year of observation, we added another 991 TOIs. So when I say TOI for the rest of this talk, it means TESS object of interest or planet candidate. So this was our prime mission count, about 2,200 TOIs just from the first 2 years of observation. And then in our third year of observation, we returned to the southern hemisphere and observed it again. And not only did we rediscover TESS objects of interest, or TOIs, that we'd seen before, we also discovered a number of new TOIs. So that brings our current count as of today to 2,647 TESS planet candidates. So in the big picture of where we're at, TESS is discovering exoplanets all over the sky and adding thousands more planets to the thousands that we already know of. So now I'm going to talk a little bit more about what it is, how we go from pixels to actual data and information about an exoplanet. So I mentioned before that TESS takes two types of data, both full-frame images and 2-minute targets. So the full-frame images, this is one that I pulled from Sector 12 from a single camera. So these are at a 30-minute cadence in the prime mission. Because our data compression was so good in the prime mission, we decided that we could go to a 10-minute cadence, so 3 times the number of full-frame images in the extended mission. So these are analyzed using an in-house pipeline at the TESS Science Office called the Quick Look Pipeline, or QLP. The 2-minute targets are analyzed by the mission pipeline of record at NASA Ames called the Science Processing Operations Center, or SPOC. And so this pipeline processes those 20,000 targets from each sector and searches for planets in those. So we have a complementary set of transit light curves from both of these pipelines. We have the high cadence, very fine-grained light curves from SPOC and the 30-minute cadence light curves from QLP. So both of these pipelines produce thousands of light curves, and these light curves can look like transit light curves, or they can look like flare light curves, depending on what's happening with that particular star. So for light curves that actually have transits in them, that there's at least 2 transits, we call these threshold crossing events, or TCEs. So we go from TCEs to an automated triage step because there's still thousands at this point. And we need a way to manage that number so that we can actually look at a manageable number visually in a finite amount of time. So we have an automated triage step that I'll talk a little bit more about in a moment. And then we go to an individual and group vetting sessions where in-person teams of people virtually look at TOI or TCEs and decide what is going to end up becoming a TOI. So automated triage, a little bit more detail. So from the full frame images and the TCEs that come from the Quick Look pipeline, we use something called AstroNet Triage. So this is a machine learning tool. It's a convolutional neural net that we take our phase-folded light curves and classify them as either transiting or non-transiting categories. This was first trained on a set of 5,000 labeled light curves from the first 5 sectors of TESS data. But since the end of the prime mission, we've been able to update that model and use upwards of 15,000 light curves from all the sectors of data. And so that is rapidly improving. For the 2-minute targets from SPOC, we use a tool that is based on the Kepler RoboVetter. This is called TESS ExoClass, or TEC. And this uses a decision tree type tool to use many metrics that are generated for each TCE to decide whether or not it's worth looking at or whether it's ruled out. So this is testing odd, even, and other common tests of whether a transiting light curve is high fidelity. So these tests give us a ranked list of TCEs, and we can go through those and vet those. So just to give you an idea of some numbers for each of these, we start with 20,000 2-minute targets. About 1,500 of those end up being TCEs. From automated triage, we get about 500. And we look at the top 200 or so in vetting. And from those, we're able to winnow it down to about 25 new TOIs from a given sector. So this is what a report looks like for one of these light curves. So to look at these objects visually, to look at the light curve, we not only have to look at the light curve as it is detrended, but also its phase-folded light curve, the secondary, and the odd even, the difference image, so if there are any nearby stars in the field. And from there, we can use this interface that we have developed to add comments, label it as a planet candidate, and rank it for the follow-up observing team to prioritize it in their follow-up queue. So what does this look like for the full frame images? It's a very similar process. However, it is at a much larger scale because the full frame images are full of millions of stars. So we start with tens of thousands of stars, light curves from the full frame images. And we're able to cut this down by about an order of magnitude in every step until we get to about 15 new TOIs from the full frame images. We find often TOIs overlap between the two pipelines, but end up deferring to the SPOC data for most of those because it is at a higher cadence. So this is what a given QLP looks like, QLP report looks like in our TED interface. So we have similar plots here. Detrended light curve, phase folded, odd even, a number of parameters, and a similar set of comets. So this is actually the report for Pi Mensa C, which was the first confirmed planet from TESS. All right. So although those two are primary sources of TCEs that become TOIs, as the community has written its own pipelines for processing the TESS data, candidates from community pipelines can also be added to the TOI catalog. So for CTOIs or community TOIs that overlap with data that we have in SPOC or QLP, we're able to inspect those asynchronously and say, okay, which of these can we make into a community TOI? So they go to these vetting steps, and these are added to the TOI catalog. So all told, we've added about 249 CTOIs over the course of the TESS mission. So now I'm going to talk, so I showed the big scatter plot with all of our TOIs on RA deck space or on the sky. So now I'd like to dive into how TOIs compare to known transiting planets in period radius space. So here I've shown confirmed planets that are from Kepler, K2, other missions in planet radius space. And so we have, as expected, a big chunk of hot Jupiters up here and another large set of longer period planets here in the smaller radius regime. So we have these. And so TESS has rediscovered about 250 of the known planets that are transiting. So these are many of the warm Jupiters that we see up here. So that was a really good test for us that early on in the mission that TESS is indeed working the way we expect it to. So also TESS had a number of predictions about what we actually were going to find. So here I have with period on the x-axis and radius on the y-axis. In dark blue, I have those confirmed non-TESS planets again, but in light blue, I have the Barclay et al. Prediction for what kinds of TOIs would come out of TESS. And this is only for stars brighter than Tmag of 10.5. I should have mentioned this before, but in the quick look pipeline, which looks at the full frame images, we only visually vet targets that are brighter than around host stars brighter than Tmag 10.5, because that just keeps the number manageable for our vetters. So we predicted that we were going to add a lot to these areas of the period radius plot and add hundreds more small planets. And also add to our set of long period planets out here. So planets with periods longer than 120 days. Up to 120 days, sorry. So what did we actually come out with at the end 3 years later? So we are finding that TESS actually is yielding hundreds more small planets. So sort of all over the place in period radius space, we're finding TOIs. And these are TOIs that have not been ruled to be false positives. So these are all still valid, active PCs. And so we'll only learn more as more follow-up is done. I'll take a little sidebar on false positives right now. So when we vet things, we label them as planet candidates, PCs, or as some other type of variability that's leading to a transit-like light curve. So something from an eclipsing binary, stellar variability, instrument noise, scattered light that is making a transit-shaped light curve, things like that. So we label those and use those in our vetting classification. So in addition to TOIs, we've also gone ahead and confirmed a lot of these test planets. So measured their mass, written up papers. So right now we're at over 100 test planets that have been confirmed, and there's more in the queue every day as follow-up goes on, precision radial velocity, photometry, spectral imaging for these targets. So again, adding some more to the hot Jupiters area up here, along with our known planets, and also contributing significantly to small short period and long period planets. So this is really exciting because it's adding more data points for astronomers interested in different kinds of population studies, formation studies. We just are adding so many more exoplanets to different demographic areas for further study. I'll add a little bit more about false positives. A lot of them are, these gray axes that I've now added to the plot. You can see a lot of these are in our hot Jupiter regime, and that's often because small eclipsing binaries look a lot like big exoplanets, so we can get duped by those. But as our reports have improved and our ability to identify whether the centroid is on target or off target has improved, we've been able to catch a lot more false positives before they become TOIs. So I'll expand a little bit more on what kinds of TOIs we found now. So TESS has found many multi-planet systems. There's about 86 that we have found so far, anywhere from 2 to 4 planets in those systems. Here I have plotted all of these systems with period on the y-axis, and I've just stacked them up by shortest period to longest period. And the color bar here is showing you in red are planets below 1.5 Earth radius. In purple are planets above 2 Earth radii. And in yellow are planets that are in that interesting radius gap of 1.5 to 2 Earth radii. So if we sort of run our eyes down this forest of exoplanet candidates, we can see that there's several systems that straddle the radius gap. And this is really interesting for folks who are interested in studying exoplanet formation. How did these planets get here? Why are their radii different? And there's also systems where the radii are all the same or very close to each other. So there's a lot of playgrounds here for studying different systems and comparing them to each other. And this is going to be really interesting as more and more data is taken for these systems. I will point out a couple of my favorite systems. One is TOI 270, which is right here. This is one of those systems where you have one planet on one side of the radius gap and 2 planets on the other side. And this is a system with a fairly quiet host star, so this is going to be very well suited to additional follow-up in the future. Another planet that got a lot of buzz at the beginning of the year was TOI 700. So this is another 3-planet system with a really unusual configuration of radii. And I'll be talking a little bit more at the end about TOI 700d, which is this outermost planet. So this is just one example of some of the really interesting results that can come from just looking first glance at what is in the TOI catalog. So I mentioned follow-up observing a little bit before. And so in addition to ground-based precise radial velocity and reconnaissance radial velocity, there is a lot of interest in TOIs that can be observed using James Webb. And what test planets will be very good candidates for observing with the James Webb Space Telescope. And this is for atmospheric characterization. So I have here a plot from the TESS atmospheric characterization working group. And so here on the y-axis, you have the equilibrium temperature of each planet. And on the y-axis, you have the planet radius. And so this is this is a binned plot. And this has a cutoff for only planets that have above a transmission spectroscopy metric of 50. So these are really high quality planet candidates, or planets for observing with for atmospheric characterization. So of the 43 TOIs that are smaller than Neptune, some of these are getting written up and have made it onto this plot. This plot includes transiting planets that were not discovered by TESS or discovered before TESS. So this is a really exciting plot to look at, because this is planets that have been proposed for James Webb, and there's almost 70 planets, transiting exoplanets, that are going to get James Webb time. So that's really exciting for better understanding and getting a really deep, close, in-depth look at the atmospheres of exoplanets that we're all looking forward to and hoping for. But as always, there's more work to do. So this is the same plot, but this is with TESS objects of interest that have not been confirmed yet. So they haven't been written up. So this is one of the many sort of to-do list plots of targets that will hopefully be good candidates for characterization. And these are all on the warmer side. So although in this sort of interesting small planet regime, these are warmer than sort of the really interesting TRAPPIST planets. So now I wanted to spend a little bit of time talking about TESS discoveries and highlighting some of the most exciting ones. So I'll start, of course, with the first confirmed exoplanet from TESS. So this was an interesting planet because it was found in a system that already had a lot of archival radial velocity data. Pymen B is a highly eccentric exoplanet that has about a 6-year period. And so to look at that star, which is one of the brightest host stars that we have with TESS, it's about Tmag of 5, and to find another really short period planet in that system was really, really exciting for us right off the bat in early August of 2018. So this is a small exoplanet, and there's a lot of interesting questions with additional follow-up that have come up of, why are these two orbits so misaligned? What happened in this planet's formation story that created this really unique system? So I think Pymen C is a really good representation of what TESS can do. It can work with archival radial velocity, it can add new discoveries, and it can provoke these new questions about what exoplanets are. I mentioned TOI 700D before. This came out in early 2020. This is a system of 3 planets. And TOI 700D is the star a little bit because this was the first habitable zone Earth-sized planet discovered by TESS. And so this is just a little bit over the size of Earth with a period of 37 days around a small, cooler star. And it's the outer planet in this 3-planet system. So although TOI 700D won't necessarily be a great candidate for additional characterization, this was a really exciting discovery, also because it was led by 2 junior scientists, Emily Gilbert and Gabrielle Suiza, as well as Joey Rodriguez. So this was really exciting because so many people early in their careers were able to contribute to this result. So TESS is finding exoplanets. The Exoplanet Archive hosts the latest confirmed exoplanets. So when papers are published, masses are measured, those show up there. But TESS has also been a surprising and rich source of non-exoplanetary discovery and other astrophysics. So because TESS is staring at the night sky for these almost 30-day periods, 28-day periods in each sector, we're able to observe transient astrophysical events and other astrophysics with stars. So TESS has this high cadence 2-minute data that allows us to get really fine-grained views of what stars are doing over long periods of time. So one example that I'll talk about that came out early this year is this system. This is the really long name, the TIC ID or TESS catalog ID for the system. This is a system of 3 binary star pairs that are all linked together in a sextuply eclipsing system. And so there's a lot of interesting questions to be asked here. So here's a graphic of what it looks like. And then I've pulled out what the report looked like for this star, what the light curve looked like. And I think I remember looking at this when this result was getting prepared and saying, wow, this is a really unique light curve. You can see all of these individual dips happening. And to go from this to picking out this sort of fully realized illustration of what's going on in this very complex system is really amazing. So in terms of stellar astrophysics, TESS is able to make these significant contributions to understanding these complex star systems. And represented by these sort of orange and white star pairs in this system, all 3 of these pairs are really similar. And so there's an interesting question here of why. Why are they so similar? How did this form? So this is one example of astrophysics that can be done with TESS. And then another example is the more cataclysmic. So this is, I'm going to try and get this to play. Might be lagging. So this is an active galactic nucleus, or AGN. Oh no, skipped ahead. All right, let's get this to play. So this is an active galactic nucleus, or AGN, called Assassin 14KO. And this has been known to flare since about 2014 in a periodic way that can be predicted. So when Anna Payne et al. Found out that this was going to be observed with TESS, there was a lot of interest in understanding what this was going to look like in the TESS data and how this could contribute to seeing both the rise time and the long tail after one of these outbursts. So what's happening here is in this galactic nucleus, there is a black hole and then a massive star orbiting that. And whenever it gets close, there's this huge ejection of matter that leads to this bright flare. So a bunch of different observatories looked at this, including SWIFT, TESS, others, and Assassin. So TESS contributed some of the sort of orange caterpillar of dots to observing one of these flares and contributed overall to modeling and better understanding the system. So TESS has also observed supernovae, other active galactic nuclei. So it's really interesting to see how TESS is going to contribute not only to exoplanets, but also to other astrophysics as years go on. So I already mentioned that in the prime mission to the extended mission, we went from 30-minute full-frame images to 10-minute full-frame images. So that was adding 3 times the data to increase the light curves coming from those images. So that was one change that happened in the extended mission, which started last July. Additionally, year 3 looked very similar to year 1, except for all of the sectors were shifted over a little bit to fill in some of the gaps left in year 1. So currently we are in sector 37, and we are almost done with this year, which is really exciting. So at the end of June, we are going to be turning over and looking at the north. So TESS has already observed 70% of the sky. With these observations in the north, we're going to bump that up to 88% of the sky observed by TESS. So in the north, we're going to be doing 2 things. We're going to be looking both at parts of the northern hemisphere that we weren't able to observe in year 2 because of scattered light. So that's what these additional sectors are going to be. But we're also going to turn TESS and try and look at the ecliptic. And this is really exciting because we're going to be overlapping with several K2 campaigns and looking at the ecliptic plane. So this will mean a lot of really exciting cross-correlation and connections made between these two missions. So I'm really excited for these sectors of observation. So to wrap up, TESS is finding thousands of worlds across the night sky. The amount of high-impact discoveries that are going to come from TOIs and the TESS Objects of Interest catalog is yet to be seen, but we're already building up a huge list of confirmed exoplanet candidates, and we're also branching out into other areas of astrophysics and observing transients and stellar astrophysics in a really in-depth way. So here are some resources for observing for where TESS is going to look next and where the data and the TOI catalog are hosted. Additionally, for folks who are interested in involving the public in observing and looking at the TESS data, Planet Hunters is a really amazing project where citizen scientists can look at TESS data, classify TESS light curves, and some of those actually end up being TOIs. So TOI 813, which was the first, which was one of the earliest long period TESS objects of interest, came from Planet Hunters. So that was TOI 813. And to dive more into the data, there's a lot of software tools here. So I will wrap up here and we can have a conversation. Thanks.
Okay, thanks Natalia for this great talk and this great overview about the fantastic TESS mission. Impressive work. Congratulations to you and the whole team on these very amazing results and all the work you've done so far. So, okay, so we still don't have any questions on the chat, so please, folks, don't be shy. Leave your questions there. And while we wait for the questions, Natalia, one thing, it's not that usual here in Brazil that we work to work with instrumentation. So someone that works directly with instrumentation. So so the people that are watching us, so they know a little bit more. Can you talk a little bit more about your role in for instance, testing the cameras and working with the instrumentation or with the computational part? So feel free to talk a little bit about more about your role, so you can encourage people to do the same.
Yes, definitely. So I mentioned that TESS has 4 wide field cameras, but these cameras are actually very small. They're maybe the size of a mailbox, like this big, and then they're like 10 centimeters in diameter. And the way that they work is that it's 7 lenses stacked up. So it basically looks like a digital camera, like a DSLR, like a bunch of lenses and then the sensor. And so this was developed in partnership between MIT and MIT's Lincoln Lab. And so my role was after the cameras had been assembled, so the lenses coupled to the detectors, seeing how the cameras would perform in space-like conditions, so under vacuum and very cold in a clean lab. And so what we did was we shone basically like artificial starlight. We used an optical bench to bounce light off of mirrors at various wavelengths in the TESS detection spectrum, so visible light, and move that all over the detector to see where the camera focus was and how the photometry changed over the entire detector. So this was painstaking work, but it was it was a lot of fun. It was really amazing to just go to work every day and realize, oh man, this is going to go to space one day. So that was really exciting.
And although it was painstaking, you were basically one of the reasons that we have TESS. So thank you very much for doing that for us. So for the exoplanet community.
Yeah, it was exciting when the first images came back and we're like, oh, did it work? Did we calibrate it correctly? And it did. It was really amazing. And it's been, the photometric performance from TESS has been really incredible.
Okay. Thank you very much. So now people are dropping the first question. So first of all, we had this comment from Mariana saying that was an amazing talk. She works with exoplanets too, so she's a student here at Valongo, and she works with exoplanets too, so she's very excited about this topic. And also, Iana is a student here at Valongo too, but she works with extragalactic astrophysics, so she was very excited to hear that we can use TESS for other scientific cases, not only for exoplanets. So she was very excited about that comment that you made. So, okay, now moving to the questions. Let's start here. Okay, I have this question from Adrian. So he wants to know how sensitive is TESS to finding planets orbiting red dwarfs?
That is a really great question. I'm so glad you asked. So TESS is optimized to look between about 625 and like, I want to say 1025 nanometers. So like in the visible spectrum, but a bias a little bit towards the red, because we know that exoplanets we're likely to see exoplanets around these small M dwarfs. And so TESS is definitely able to image those. And so a lot of the exoplanets that we've been focused on and that many people are interested in studying with TESS are orbiting M dwarfs. So it's definitely a major focus of data analysis, and many guest investigators for TESS have proposed that the 2-minute targets be around on catalogs of M dwarf stars.
Okay, thanks. The next question is from Thiago. He thanks you for the talk. And one thing that he was not sure about, are all objects within the field available in the database, or are the light curves available only for pre-selected objects?
Yeah, so I can talk about that. So the archive for all of the TESS data is MAST, or the Mikulski Archive for Space Telescopes. So that's hosted by the Space Telescope Science Institute, and they also have the data for Hubble. So what we sent them are all of the TESS full frame images so that's like the entire time series. And so for a given target, you can pull out the time series of any star that TESS has observed. And there's a tool that they have for that called TESS Cut. So you can use that to pull out the light curve for any star you're interested in. And then for the pre-selected 2-minute targets, yeah, those are selected in advance and those get the 2-minute data.
Well, okay, thank you very much. So now we have this question here from Mariana. I mentioned she works with exoplanets, and actually she's working with me, and we're working on secondary eclipse. So that's the reason for this question. Do you have secondary eclipse data in the TESS objects of interest catalogs?
So do you mean like, can we see the secondary for like, okay.
Yeah.
So yeah, in the light curves, you can often see like the secondary eclipse for like the hot Jupiter type exoplanets. And there's some work. So Avi Spohr has been looking at the phase curves for like WASP planets that have TESS data because you can see the secondaries really nicely in those. And so I showed a couple of screenshots of the vetting reports for TOIs. So in those vetting reports, it shows both the primary and it phase folds to look for the secondary. So we do examine when we're about to release something as a TOI, whether or not it has its secondary. So are you guys looking at trying to find like eclipsing binaries, or is this like to look for planets with deep secondaries?
Yeah, it's a secondary eclipse for hot Jupiters. Yeah, so we're investigating the influence of the stellar activity on the atmospheric profiles of the planet. So that's the reason for her question. So she might be looking for more data.
Yes. So it depends on like how deep the secondary is for whether you can pick out like more like low SNR features within the secondary. But I think we do have candidates. So look for like Spohr et al. For some of those phase curves. And I think Ian Wong as well has written some papers on that.
Okay, great. Thanks, Natalia, for giving us more work to do and more data to work with. Thank you very much. That's great.
Anytime.
Okay, so here we have another question from, so Iana wants to know a little bit more about the AGN observations. So can you tell us a little bit more, and maybe how the dust obscuration can affect this process?
I can talk a little bit about this. So for AGN, so I think we've seen I have seen across my desk 2 papers on AGN observed with TESS, and there's some specialized searches that are looking for TESS transients. Because we were really lucky with Assassin 14 KO because the team knew that it was going to flare in this periodic way and they could predict when it was going to happen. But otherwise, you have to like set up a difference imaging pipeline and look for transients that way. So there's a couple of teams that are doing that with test data and like working in partnership with Assassin and other transient searches. So like the Zwicky Transient Factory, Assassin, places like that. And so to answer the second part of your question, I would imagine dust obscuration would change whether you get like a nice clean pulse shape or whether you get something a little bit messier. A related topic is another exoplanet, not quite an AGN, but AU-MIC was this kind of high-profile exoplanet discovery last year, where it was an exoplanet inside a protoplanetary disk. So it wasn't a typical nice, clean transit light curve. The team looking in that sort of protoplanetary disk had to be aware of that in their search. So theirs was a bit more manual.
Okay, thanks. So Iana, I can feel you. I can feel you slowly drifting into the exoplanet community. So join us. So please look at the test data for AGNs, and maybe you'll fall in love with exoplanets. Okay, so moving on to the next question. So Elielson wants. So first, he thanks you for the great presentation. And he wants to know what's the expectation for transiting planets around binary stars with TESS?
Another great question. So TESS has found a few examples of circumbinary exoplanets. So one that I can think of is TOI 1338, which was a TOI found in a long orbit. I think it was something around 80 days around a 2-star system. And this was actually a really interesting system because the story behind it I really like. It was a high school intern working at the NASA Goddard Space Flight Center who was looking at transit light curves by eye and noticed that there was like the periodic star transit, so those orbiting each other, but then there was this like odd transit that kept happening every so often, and realized, oh, hey, this is an exoplanet. And that became TOI 1338. So it's really amazing how in this field, even junior astronomers can make these massive contributions. So that was a really exciting discovery for that reason as well.
Great, thanks. And thanks also for motivating our students. So you see, guys and girls, so junior students can really participate in huge discoveries with the latest mission. So that's a nice inspiration for you all. Okay, so while I wait for maybe, we don't have any more questions so far, so I'll get some time for people to think while I ask one question. So what is the deal with all those planets, like Neptune planets at short orbital periods that we haven't seen before, and now we are maybe seeing them with TESS? So can you say something about that, or maybe is some research that you cannot talk about? Is anyone looking at those?
I think that's a great question. So I am not specifically one of the people who's like super interested in cool or hot Neptunes. So I can't comment in depth, but I think that's one of the great things about the catalog is that we did notice like, oh, hey, we're filling in these empty spaces, or these spaces where we didn't have things. And so that's part of what follow-up is doing, is for targets around well-behaved stars or in fields that aren't crowded with other stars. Once follow-up gets started, folks can start looking in more depth at these cool Neptunes, or like looking in the Saturn desert. That's another area that's of interest. And trying to figure out, like, okay, is this a function of the telescopes not being able to detect this, or not looking at this at the right cadence, or is this a function of a true scarcity? And so I think like exoplanet demographics is definitely exploding, and I'm so excited about that.
Yeah, it's impressive because actually Kepler reviewed this whole population of planets between Earth and Neptune sizes, and now TESS is revealing this new population. So it seems that every mission that we have, we see we populate a new region of the radial spirit space. It's actually amazing. So that's very interesting. And by the way, the plot that you showed with the systems that TESS discovered, it's really beautiful. So you can really see the architectures there, and I work with planetary architecture, so it's very, very nice to see those. So beautiful plot too.
Thanks.
Okay. So guys, last chance guys and girls, last chance to put your questions there on the chat. Meanwhile, I'll ask one more. So I noticed also that in the demographics plot, TESS still haven't found not so many Earth-like planets as Kepler. Is it something related to the mission, or is just because we don't have enough data or coverage, or do you know the reason for not finding Earth-like planets? Not many as Kepler so far.
It's something that we're definitely starting to ask, and yeah, I think like taking a moment to like look back at the like period radius plot is like, oh hey, like why don't we have these? So I think part of it is in vetting, we're looking for the things that are easiest for ground-based follow-up. So this is mostly targets brighter than Tmag 10.5, things that go down to about test magnitude of 13.5, but around 12 is where it starts getting tricky for radial velocity that's ground-based. So part of that is I think that M-dwarfs can be fainter. And so if you're looking for Earths around those, like that's going to be a really shallow transit. But this is part of what's exciting, is that like in the TESS team, we have a postdoc, Michelle Kunimoto, who's working on searching that our quick look pipeline that curves between 10.5 and 13.5, and finding more TESS objects of interest around those fainter stars. And as more people go over the data sets with a finer and finer tooth comb, I think we're going to find more of the smaller and more interesting planets and like low SNR planets.
Great, thanks. Hopefully we find those two in TESS.
Yes.
Okay, so I don't see any new questions popping up on the chat, so I'm just gonna show you some message that we have from our audience. So Karin says, very cool work. And Mariana thanks you for the talk, and so does Elio. And Eli also say thanks for your answer to his question, and also for the talk, I guess. And before we wrap up, it's really cool to see a woman in science being so successful and having a leadership position in such an important mission as TESS. So can you say something to our female students in the audience that you might think that's nice to share with them, so they can get inspired to go on with their careers?
Of course. First of all, you can do it. You belong here. I was very fortunate in TESS to have an amazing group of mentors. In particular, Sarah Seeger, who is the TESS Deputy Science Director. The TOI project was part of the TESS Science Office, and she guided how the TOI catalog was formed, and I learned so much from her in the early years of TESS and as we got the catalog to where it is now. And so she was an incredible mentor and has shared so many opportunities with me. So I would say finding mentors who support you and want you to succeed is so valuable. And the TESS group has been really amazing and supportive. So I think I would say find a group where you feel like you belong and where you can thrive and do your best work and show everybody the amazing scientist that you are.
Okay, perfect. Thank you very much. And by the way, for those who are watching, we also had Sarah Seeger in our seminars last year. So you can, it was an amazing talk. So you can find the seminar on our videos on our YouTube channel. So just check them, check the videos, and you'll find Sarah Seeger there. There is a playlist. Actually, there's a playlist with our seminars and Sarah Seeger's, and all other amazing talks that we had so far are there. So Natalia, thank you very much for this great overview about the TESS mission. And please send our thank you and congratulations for the whole team you work with. And thank you very much for showing these incredible results. I hope we'll have you in the future talking about the next data releases from TESS with lots of new interesting planets. And thank you very much for accepting our invitation and for giving this great talk to us. Do you want to say anything else before we wrap up?
Thank you for hosting me. This has been amazing. I'm so excited to see all of this engagement, and yes, go TESS.
Yeah, go TESS, definitely. And Iana, thanks to you also for the very nice work. So, well, this brings us to the end of our talk today. Thank you very much for watching us. And please stay tuned in our social media so you can get the notifications for the next seminars and next speakers. We have a really cool lineup of speakers for this semester. So stay tuned, follow us, and hope you all have a great rest of the week. Thank you very much. Stay safe. Bye-bye.